This video is on the use of product rules for radicals. So we all know what a radical is. It is the nth root of a number. So we know the nth root of A is A raised 1 over n, and the nth root of B is B raised 1 over n. So if we multiply those together, we have A raised 1 over n times B raised 1 over n. Since the bases are different, but the powers are identical, we could simply write it as AB raised 1 over n, which simply is the nth root of AB. That simply is the product rule. So we can only combine this if we have different bases. But they have identical exponents. So in this scenario, we have the bases as A and B. The exponents for both A and B are 1 over n. So here we have square root of 3 and square root of 5. So I combine the square roots and simply write it as 3 times 5 because we have different bases. A is 3 and B is 5, but identical roots. So that would simply give us square root of 15. Again, in the next one, we have the third root of 4 and the third root of 2. The roots are identical, so I could simply combine them and write it as the third root of 4 times 2, which is simply the third root of 8. We should always ask the question if we can simplify once we combine the roots. Here, I could write A as 2 cubed as a power of 3. You may ask me, well, why would he want to write it in the power of 3? Because it is the third root, and if I write whatever that is inside the root in terms of powers of 3, then there is a possibility that I could cancel things out. So I could rewrite the root as 2 raised 3 raised 1 over 3. I could now multiply those two terms, which would give me 2 raised 3 times 1 over 3. The 3's would get cancelled. I would get 2 raised 1, which is simply 2. Here we have identical roots, so we are going to simply combine them and write it as 2 over A times B over 3. Since we are multiplying, we multiply the numerators together, we get 2B. We multiply the denominators together, we get 3A. Just like the product rule, we have the quotient rule. The idea is the same. If we have different bases, but identical roots, we could write it as A raised 1 over n divided by B raised 1 over n, which would be A over B raised 1 over n, which simply is the nth root of A over B. Keep in mind, we could only do this if we have different bases and identical roots. Now, you may ask me, well, could we have the same base and, get away with this? Of course we can, and things would just, get simplified, and you'd have A over A, and it would simply become 1. So the most important aspect here rather is the identical root part. So we have square root of 5 over square root of 16. We could split it up and write it as square root of 5 divided by square root of 16, which is square root of 5 divided by 4, and of course it would be plus or minus. In the next problem we have square root of 40 divided by square root of 81. I could write this as square root of 40 divided by square root of 81. The denominator is easy, it's simply plus or minus 9. Could we simplify the numerator? We could write the numerator as 4 times 10 divided by plus or minus 9. Now, if we use the product rule, since 4 is multiplied to 10 under the same root, which is the second root, I could split it up and write it as square root of 4 times square root of 10 divided by plus or minus 9. Square root of 4 is simply 2. And plus or minus over plus or minus, it still is plus or minus 2 square root of 10 over 9. Some might say, well, should we put that plus or minus? Is it necessary? Well, technically speaking, it is plus or minus, but sometimes the solution might simply ask for a positive value. It depends on the problem. So here we have to use quotient rule to simplify, and we are making an assumption that all variables represent positive real numbers. So whatever we have inside the x here is a positive real number. So since we have 27 over 64 under a common root, which is the third root, we could split it up and write it as cube root of 27 over cube root of 64. But 27, we could write it in a power of 3. Why do I have to write it in a power of 3? Again, it's the third root. If we had the fourth root, we're going to try and write the number, whatever that is inside the root, in powers of 4. So 3 cubed is 27. In a similar manner, 64 is 4 cubed, but we know we could write the root as 3 cubed over 1 raised 1 over 3, and 4 cubed raised 1 over 3. Those two would get multiplied, those two would get multiplied, and we would simply have 3 raised 3 over 3 divided by 4 raised 3 over 3, and the answer is 3 over 4. We could split the fifth root and write it as the fifth root of 7 divided by the fifth root of 32x raised 5. We can't write 7 as a fifth root. Well, we can, but it is not going to be an integer, so we're going to leave that as is. But I could split up the root in the denominator as the fifth root of 32 multiplied by the fifth root of x raised 5, which is the fifth root of 7 divided by the fifth root of 32 is simply 2 raised 5. So we have the fifth root of 7 divided by 2, excuse me, 2 raised 5 raised 1 over 5 times x raised 5 raised 1 over 5. And when we multiply those two terms, we would simply have 5 over 5, which is 1. So the answer would end up being the fifth root of 7 divided by 2 times x. So here we want to simplify radicals. So square root of 40, we can first write it as square root of 4 times 10. You may once again ask, why does we want to write it as 4 times 10? Could you not write it as 8 times 5? But I'm trying to write it in powers of 2 so that the square root can cancel the power of 2. So I use the product rule to split the root. And 2 raised to raised 1 over 2 times square root of 10. So if we put plus and minus, it is 1, 2, and the 2's would go away. Okay, we're multiplying the powers. 2 raised 1 is simply 2 multiplied square root of 10. Square root of 300. I want to write 300 using a power of 2. So let's say we could write 300 as 100 times 3. I can split it up and write it as square root of 100 multiplied by the square root of 3. One of these terms definitely can be written in terms of a square. 100 is a perfect square of 10, so we have 10 squared times root 3, and recall these two sort of go away. I've given the reasons earlier. So we have 10 times square root of 3. Square root of 15. So could we simplify this? The question can be answered by asking another question. Is or are there factors of 15 that are perfect squares? Square root of 15 has, or 15 has factors 3, 5 and 1. So we can write it as 3 times 5, and neither 3 nor 5 are perfect squares, so we cannot simplify. So the answer here is no. That's the best we could do. We could leave it as is. Here we have the cube root of 16. So could we write 16 or factors of 16 in terms of a perfect cubed? Y cubed, this is the third root. So 8 times 2 is 16, and 8 is a perfect cubed of 2. So I could write it as 2 cubed times 2. Now I could split the roots using product rule. So the third root of 2 cubed multiplied by the third root of 2. Those two go away, and we would simply have 2 square root of 2. Quotient rule, in the next problem, we could split it up and write it as the cube root of 3 divided by the cube root of 64. Could we write 3 as a power of, or the cube of some number? We cannot, so we can just leave it as is. We can, but it's not going to be an integer. We want to keep it as an integer. So the cube root of 64 can be written as the cube root of 4 cubed. And 4 cubed is a perfect cube. So those two would go away. We would simply have the cube root of 3 divided by 4. The square root of x raised 7. So here we want to know if we could write x raised 7 in terms of a perfect square. So I could write x raised 7 as x raised 6 times x raised 1. Bases are identical, add the powers, 6 plus 1 is 7. We could split up the two factors and write it as square root of x raised 6 times the square root of x. Is x raised 6 a perfect square? I could write it as x cubed raised 2. We multiply 3 and 2 to get 6 times the square root of x. The root and the square would get cancelled, and we would simply end up having x cubed times square root of x. In the next problem, first let us split the numerator and the denominator because they are under the common root, which is the square root. Could we write 20 in terms of a perfect square? We could write it as 4 times 5. Is the denominator perfect squared? Indeed. I could write it as x raised 8 raised 2. 8 times 2 would give us 16. Split the roots in the numerator using product rule. We have square root of 4 times square root of 5. In the denominator, those two would go away and we would simply have x raised 8. And we know square root of 4 is 2. So we have x raised 8. I'm sticking with positive numbers because at the beginning of the example it said they're all positive real numbers, so I'm just going to stick with positive. And now we have a cube root, so the question is, could we write whatever term that's inside the root in powers of 3? But before we do that, to make things easier, let us split the root. So could square root of 54 be written in terms of a perfect cube? I could write it as 27 times 2. I could write x raised 6 as x squared raised 3, which gives us a perfect cube. And at the beginning it might seem that 8 is not a cube, but if I write it as y raised 6 times y raised 2, the bases are identical and 6 plus 2 would be 8. So let's split up all the roots. So cube root of 27 times the cube root of 2 times the root and the power would go away. So I have x squared, split the root, cube root of y raised 6 times the cube root of y squared. Is 27 a perfect cubed? Yes, indeed. So we could write it as 3 cubed and cube root of 2 times x squared. Could we write y raised 6 as a perfect cubed? We can. It is simply y squared raised 3 2 times 3 would give us 6. And cube root of y squared. Those two go away, and those two go away. So we would have 3 times the cube root of 2 times x squared times y squared times the cube root of y squared. So the 3, we can't do nothing about it. We can bring the roots together. We could put the variables together. I'm trying to simplify this expression. Since I have identical roots, I'm going to revert back to combining them and putting it under the common root. That's the product rule. And since I have different bases, identical powers, I could put them under the same power. So I have x, y raised xy raised 2. So we are going to use quotient rule to divide here. Could we write square root of 20 in terms of a perfect square? 20 is 4 times 5, divided by square root of 5. Split the roots in the numerator. We have square root of 4 times square root of 5, divided by square root of 5. Those two would get cancelled, and square root of 4 is simply 2. So now we have 48, but before we get to that, since we have multiple terms, let's go ahead and split the root. We have 7 cube root of 48 times the cube root of y raised 4 divided by the cube root of 2 times the cube root of y. So we have 7 times. Is it possible to write 48 in terms of a cubed? So the only way would be to write it as 8 times 6, because 8 is a cube, a perfect cubed, and it would be 2 cubed. Is it possible to write y raised 4 in terms of a perfect cubed? I can if I wrote it as y cubed times y. There is nothing I could do about the cube root of 2. I'm going to keep that as is. And I have the cube root of y. So split the root in the numerator. 7 cube root of 8 times cube root of 6 times the cube root of y cubed times the cube root of y divided by the cube root of 2 multiplied by the cube root of y. So the root gets cancelled there. Those two are identical terms. That goes away. So we have 7 multiplied by the cube root of 8. 8 is 2 cubed times cube root of 6 divided by cube root of 2. those two go away, so we have 7 times 2 times the cube root of 6 divided by the cube root of 2. Since we have division, we should ask the question that could we simplify things furthermore? So we have 7 times 2, which I could write it as 14. The denominator is cube root of 2. Is it possible for us to get a cube root of 2 in the numerator? It is feasible, because I could write cube root of 6 as cube root of 2 times 3. So we have 14 cube root of 2 times the cube root of 3 divided by the cube root of 2. Those two terms are identical, they go away. And we would simply have 14 multiplied by the cube root of 3, and that is the final answer. So here we have the distance and midpoint formulas, and we're going to talk about the distance formula here because it involves the square root. And it goes back to the Pythagorean theorem, which if we have a right angle triangle and we have distance or lengths A, B and C here, then C squared is simply A squared plus B squared. So we can extend the concept to find the distance between two coordinates in the coordinate plane. The first point being x1, y1, the second point is x2, y2. The formula here is quite simple. We have x2 minus x1 squared y2 minus y1, the entire thing squared, and we take the square root. So we have our first coordinate in this example, which is x1, y1. The second coordinate is x2, y2. So the distance would be square root of x2 minus x1 squared plus y2 minus y1 squared, which would be equal to the square root of minus 2 minus of minus 5 plus y2 is 2, y1 is 8. So we have square root of negative 2. Negative times negative 5 is positive 5. 2 minus 8 is negative 6. Negative 2 plus 5 is 3. Negative 6 squared. 3 squared is 9. 6 squared is 36. And we have square root of 45. Now, it is always good to ask the question, if we could simplify this further, as we saw earlier, we can do it if we can write 45 or its factors in terms of a perfect squared. Here we could write square root of 45 as 9 times 5. 9 is a perfect squared. So let's split the roots, write it as square root of 9 times square root of 5. So square root of 9 is square root of 3 squared times square root of 5. The root and the power would go away. So we have 3 times square root of 5. The midpoint formula is much more simpler compared to the distance formula. So if we have 2 points, the x, y x1, y1 and x2, y2, all we do is add the x coordinates, divide by 2, add the y coordinates and divide by 2 to get the midpoint between 2 points. So here, let me just graph so let me make a note with the distance here also. What does it mean to find the distance? So we have a point -2 and 2, which is right over here. That is -2, 2. And we have another point -5 and 8, somewhere over there. So the distance between those 2 points is simply d, which is 3 square root of 5. Simply the answer that we found here. So using the same argument, let me start with the graph here. So if we have 2 points, the same 2 points, which is -2 and 2, and we have -5 and 8, which should be right over there. So -5 and 8, and that is a line segment between the two, and we want to find the midpoint. The midpoint is a point that's over there, and we'd like to know what that point is. To find that, we simply add the x coordinates, x1, y1, x2, y2, add the x coordinates, divide by 2, add the y coordinates, divide by 2, so -2 plus -5 divided by 2, 2 plus 8 divided by 2, so we have -7/2, 10/2, which is 5. And we can verify the answer because 5 is somewhere over here, and -7/2 is -3.5, which is over there. So we did, in fact, find the midpoint.